How can we say where that point is? And I don't mean somewhere a bit left and a bit up from the middle of the screen. I want something rather more accurate than that. So how can we describe the position of that point accurately? Well, I expect that you might be thinking a little bit of the distance from the edge and the distance up from the bottom. In other words, something rather like Cartesian coordinates. And with Cartesian coordinates, we normally have two axes, and I've drawn them there for you. So there is your conventional, normal way of describing the position of a point on a plane. How else could we describe the position of that point? Well, we could decide that we didn't need to have our axes at 90 degrees. And I could describe the position of that point as so much in this direction, and then follow the other one parallel up so much in that direction. So that's another way of looking at describing the position of the point. How else could we describe the position of that point? To describe the position of the point, we do need to start with some framework. We've just had Cartesian axes and then axes which were at an angle, not 90. If I start with this framework, I could say where this point is by measuring the distance from A and the distance from B. And you can see you could take out your compasses, you could actually find the distance of the point. That would be a little bit awkward, because the point down here would have the same two distances. So we'd have to have some convention for knowing whether we were above or below. How about another way of thinking of where that point is? I could think of taking two fixed points, A and B, and the line between them, and measuring the angle anti-clockwise with the line from A and the angle anti-clockwise from the line in the same direction from B. So there is another way of describing where that point is. There will be many more, if you are really inventive, that you could think of to describe where the position of a point is on a plane. However, none of these are what we are going to look at in the next chapter. We are going to look at something called polar coordinates. Here, our framework is a line, usually drawn in the direction of the positive x-axis, together with a point, and that is the pole. Polar coordinates, there is the pole. And here is your initial direction. Then if we take a point P, we can draw a line from O to P and measure the distance r, and we can measure the angle anti-clockwise from the initial line. That will give you unique coordinates r and theta, provided that we take r greater than or equal to 0 and 0 less than or equal to theta less than 2 pi. We can convert from polar coordinates to Cartesian coordinates if we think of this initial line as the x-axis and the perpendicular line as the y-axis, and vice versa. It's very similar to converting complex numbers from x plus iy to r cos theta plus ir sine theta, or in the other direction. In this case, we have x is r cos theta and y is r sine theta. Some books, most books, allow r to be negative. Autograph, the graph plotter which I use, draws a dashed curve when r is negative. Now let's look at some simple polar curves, polar equations, and their Cartesian equivalent equations. If I start off with r equals 5, I think you all ought to be able to see what that is. If I have a point and a line, the distance from the point is always 5, I must have a circle. The initial line would be the x-axis and the origin, the point O. R is then always 5. So we should be able to write down the Cartesian equation without doing much work. We know the equation of a circle, center the origin, radius 5 is x squared plus y squared equals 5 squared, which is 25. Let's have a look at another one. R equals 2 plus cos 2 theta. How are we going to find the Cartesian equation of that? We haven't got a nice obvious curve like we had last time. What can we use? Well, we can remember that x is r cos theta and that y is r sine theta. How is that going to help us? Well, you should be able quite quickly to notice that cos 2 theta is 2 cos squared theta minus 1. And that helps us because x over r is equal to cos theta. So I now have that r is 2 minus 1, which is 1, plus 2x squared over r squared. Multiply both sides by r squared. Sorry, r cubed. And of course, r is the length of the line. Pythagoras tells us that r squared therefore is x squared plus y squared. Or you can do it from the equations at the top, r squared cos squared plus r squared sine squared. So r cubed is x squared plus y squared to the 3 over 2. R squared is x squared plus y squared. If I then add 2x squared, I get 3x squared plus y squared. And here is the curve. A nice simple looking polar equation and a rather much more complicated, unpleasant looking Cartesian equation. Sometimes it's not at all easy, if possible, to go from polar to Cartesian. Okay, let's have a look at another one. R squared equals sine 2 theta. Well, I think having just done the one before, we will be looking at 2 sine theta cos theta. Sine theta is y over r. Cos theta is x over r. Multiply both sides by r squared, we get r to the 4 is 2xy. R squared as before, Pythagoras gives us x squared plus y squared. And so we have x squared plus y squared, all squared is 2xy. Let's have a look and see what that one looks like. And there we are. Again, a nice polar equation and a less pleasant, not as nasty as the last one, but a less pleasant Cartesian equation. Well, what happens if we start with a Cartesian equation and want to find the polar equation? So let's start with this one. Nice, easy-looking equation. Y equals 2x minus 1 is a straight line through minus 1 on the y-axis, gradient 2. How are we going to turn that into a polar equation? Well, this is very simple. We know that y is r sine theta and that x is r cos theta. And so we have r sine theta is 2r cos theta minus 1. A little bit of playing around will give us r is 1 divided by 2 cos theta minus sine theta. Yes, I think I prefer that equation of a straight line to that one. Now if we look at the equation of an ellipse, x squared over 4 plus y squared is 1, gives us this ellipse. And you've seen the secret in the previous example. X equals r cos theta, y equals r sine theta, and therefore r squared cos squared theta over 4 plus r squared sine squared theta is 1. Multiply both sides by 4 and divide by cos squared theta plus 4 sine squared theta. So there is converting a Cartesian equation to a polar.